So today's webinar will be about thermoelectrics, the basics of them, and with which instruments in our product lineup you can measure different thermoelectric properties. So about me, I'm Erika. I studied physics in Erlangen in Germany, and I'm working for Linseis since 2020. And at Linseis, I'm responsible for the thermal transport measurements in the application laboratory. So today's webinar will be first about thermoelectricity, some definitions of different properties. For example, the Seebeck coefficient and the t-value, the figure of merit. Then I will show you the product lineup for thermoelectric applications, which are useful, which are good add-ons, and so on. And in the end, I will show you some application examples of measurements we did here with our instruments. Thermoelectricity in general describes the direct conversion of a temperature gradient into electricity and vice versa, and is based on the three thermoelectric effects: the Seebeck effect, its reversal effect, which is then called the Peltier effect, and the Thomson effect. The direct conversion means that no conventional heat engine with moving parts, which needs maintenance, are required. Thus, thermoelectricity has a big potential for many kinds of everyday applications. Next to already established thermoelectric applications in the aerospace industry and laboratories, current hot topics are the waste heat recovery from hot engines and combustion systems, which could save billions of dollars if it could be captured and converted into electricity via thermoelectric devices, especially in regards of power plants or, for example, cars. Another very recently hot topic is the Internet of Things, where remote devices like autarkic sensors and actors require autonomous power sources. Furthermore, thermoelectricity can be used as sensors for temperature determination. Here you can see an example of an LFA sample holder. The white thing here in the middle is a thermal element which determines the sample temperature. Generally, if one talks about thermoelectric phenomena, or in particular thermoelectric generators, it is often referred to the usage of the Seebeck effect. The Seebeck effect generally describes how a temperature difference along a conductor creates an electric field and, in consequence, the so-called thermal voltage. The basic effect can be explained using here this illustration, where we see a conductor, for example, a typical thermoelectric material like bismuth telluride, which gets heated on one side, here on the left, and stays cool on the other side, here the right side. Because of the introduced heat on the left side, the cold charge carriers can move back. And in average, this means that charge carriers from the hot side diffuse to the cold side until, in consequence, an electric field is built up, which acts against this movement. And the size and direction of this electric field depends on the charge carriers on the hot side, which move to the cold side. So the electric field thus depends on the material and temperature, which means that the Seebeck coefficient is a material-specific and temperature-dependent parameter. The Seebeck coefficient is given in volt per Kelvin, or more often seen in microvolt per Kelvin. So metals possesses only a small Seebeck coefficient of a few microvolt per Kelvin, whereas, for example, semiconductors can have a Seebeck coefficient of several hundreds of microvolt per Kelvin. Now, if we want to look for promising candidates for thermoelectric applications, we need materials with a high conversion efficiency, and we need a way to compare the suitability of different candidates. For this reason, the thermoelectric figure of merit has been introduced. The figure of merit is also shortly called a ZT value. The ZT value consists of the Seebeck coefficient, the electrical conductivity, and the thermal conductivity. The aim of finding a good thermoelectric material or to generate one is to maximize this figure of merit. So from this formula, it can be directly seen that for high conversion efficiency, one needs a high Seebeck coefficient, a high electrical conductivity, and a low thermal conductivity. And the electrical conductivity needs additionally to be big enough to drive a sufficient current, and the thermal conductivity needs to be small enough to allow the build-up of a sufficient temperature gradient along the sample. So it is not so easy to find a good material since the electrical conductivity and the thermal conductivity act, so to say, against each other according to the Franz Wiedemann law. The most common way to determine this figure of merit is to measure all single properties here separately and calculate afterwards the ZT value. For the Seebeck coefficient and the electric conductivity, one can use a 4-point probe setup in combination with thermocouples, like it is used in our system called LSR. And for the thermal conductivity, the lambda, here on the bottom, one can use, for example, the laser flash technique. But the laser flash only determines the thermal diffusivity, which is called alpha. Thus, one needs additional information about the specific heat and the density of the sample. The specific heat can, for example, be measured using also an LFA or a DEC. However, one can also measure the ZT value directly. For that, one can use the Harmon technique. This can be also used with the LSR setup with a patented sample holder. So this can be a powerful tool to directly measure the ZT value since one reduces the errors of the single measurements, so to say, which add up in the end by calculating the ZT value. So this direct measurement of the ZT value can be a powerful tool, but is applicable only for a small amount of samples and is limited in temperature range. So that I will come a bit later more specifically. In practice, the conversion of heat into electricity is not performed by a single element, but by thermoelectric modules. If many thermal elements, usually varying P and N type materials, they are connected thermally in parallel and electrically in line. And this setup is then called a module, which can be seen here in this illustration. These modules can either be used for the conversion of heat into electricity, then they are called thermoelectric generators, shortly TEG, or these modules can be used as a heat pump in order to create a heat flux. In this case, it is then called a Peltier element. Peltier elements are often used for temperature-sensitive applications, like in lasers or in laboratory environments, for example, in experimental setups. The thermoelectric conversion of conversion efficiency, this one here of a module, can theoretically be calculated using the average ZT values of the N and P type legs, which is shown here with this formula. And another way would be, what is more practically, measuring the electrical power output at a given thermal load. So shown here with this formula. Next to the maximization of the thermoelectric conversion efficiency, material stability, costs, and toxicity are in the aim of research and quality control. For this task, Linseis has the most comprehensive and advanced product lineup worldwide. We are partners of institutes, universities, and companies since more than 60 years and have a focus on thermal electrics with the most innovative concepts since more than 10 years. So we have a broad product lineup for determining the thermoelectric properties of legs or the thermoelectric generators. So for the legs, one can, for example, use the LFA in combination with DSC for determining the thermal conductivity, the LSR, the LZD, the HCS, and for thin films, the TFA and TFLFA. For the thermoelectric generators, one can use the TEG tester or also the LFA for example, determining the properties of the ceramic plates on top and on the bottom. So these tests are possible from cryogenic temperatures up to 1,500 centigrade from bulk to nanometer size thin films using the different instruments. So with these instruments, one can cover a lot of different applications of thermoelectric materials. So now we come a bit more into detail of the different instruments which can be used to determine thermoelectric materials. And we start with the thermal conductivity. As already mentioned, the thermal conductivity can be determined using the LFA. And the LFA firstly measures only the thermal diffusivity. And using that and the p-value and the density of the material, one can then calculate the thermal conductivity. So how does an LFA work? One has a sample which can be square or circular shaped, and we have a power source, either a xenon lamp or a laser. This power source puts then a light or laser pulse onto the complete surface of the sample. Sample absorbs all of the energy, and then a detector measures the temperature rise of the rear side of the sample with temperature. So the signal looks like that. So here you can see the temperature rise of the backside of the sample in dependence on time. And to determine then the thermal diffusivity, one needs T1/2. This is the time where half of the maximum is reached. And for the calculation for the thermal diffusivity, one additionally needs the thickness of the sample. The big advantage of this technique is that it can be used for a very broad range of applications, from cryogenic temperatures up to 2,800 centigrade Celsius for bulk materials and also for micrometer thick films. Furthermore, one can test samples with a low thermal conductivity and with a very high thermal conductivity like diamonds. However, on the backside, the LFA technique measures, as already mentioned, only the thermal diffusivity, but not the thermal conductivity directly. Nevertheless, both properties are linked with this formula, so this is a good way to determine the thermal conductivity in such high temperature ranges. The next instrument which is useful to determine thermoelectric materials or properties is the LSR. With the LSR, one can measure the Seebeck coefficient and the electrical conductivity of the material. So the LSR platform is the standard instrument for the characterization of these properties. And for the Seebeck coefficient measurement, one places a sample in between two electrodes. These electrodes shown here contain also heating coils, and with these one can generate a predefined temperature gradient over the sample. Furthermore, one has two thermocouples here on the side, which touch the sample and measure the real temperature gradient over the sample. And additionally, with those thermocouples, one measures the thermal voltage, denoted here by VTH. And using these values, one can then calculate easily the Seebeck coefficient. So using the thermal voltage and the determined temperature difference along the sample. For the resistivity measurement, a DC for terminal measurement technique is used, like shown here in the picture. For the measurement, one impresses a constant current into the sample using those two electrodes, and the resulting voltage drop over a portion of length, here denoted by T, is then measured using, again, those thermocouples. For the calculation of the resistivity, one uses then this formula using all of the properties which I mentioned, mentioned, and additionally one needs the cross-sectional area of the sample. So this measurement of the resistivity can then be used to calculate the electrical conductivity of the material. And a big advantage is that the Seebeck coefficient measurement and the resistivity measurement can both be determined in one run. So in summary, so to say, the LSR can be used to characterize the Seebeck coefficient and the resistivity and the electrical conductivity of a broad range of samples, from which can be bar-shaped or a disc. The disc can be additionally also used then for the LFA to determine the thermal conductivity. Furthermore, with the LSR, one can also measure thin films. And this platform generally can be equipped with a low temperature furnace for measurements under cryogenic temperatures, or several high temperature furnaces, which are either optimized for fast heating and cooling rates, or for a maximum temperature of 1500 centigrade Celsius. And in addition, we offer also a high resistance add-on, which allows the characterization of high resistive materials. Also a camera option for the highest accuracy, resistivity measurements, and many different thermocouple options for all kinds of Seebeck coefficient measurements, as well as the patented Harmon adapter for the direct ZD determination according to the Harmon technique. For the Harmon measurement, a current is impressed into the sample with two needle contacts, as they are shown here in this image. And due to the Peltier effect, so the converted Seebeck effect, so to say, one of the transitions is locally cooled or heated, and thus a temperature profile is established. And if then the ratio of the measurement of the initial voltage drop, so the ohmic part without a temperature gradient, and the measurement of the stationary voltage drop, the one including the thermal voltage, are used, one can calculate the figure of merit directly as it is shown here in this formula. Advantages of this Harmon method is that the measurement error is smaller due to only one measurement, with several measurements of the Seebeck coefficient, the conductivity, and the thermal conductivity, the errors of each single measurement add up, so thus the error will get larger. However, the disadvantage of the Harmon method is that one can only measure good thermoelectrical materials and maximum up to 400 centigrade Celsius. This product lineup, which I showed until now, is rounded off by the highly integrated LZT platform. This one combines the LFA with a laser source and the LSR unit in one. So with this instrument, one can measure the Seebeck coefficient, the electrical conductivity, and the thermal conductivity all in one. So this is a powerful tool which saves costs and also lab space, and is ideal for the research community where a high sample throughput is less important. Since, for example, with the LFA, one can measure up to 6 samples at the same time. So measure the thermal conductivity of 6 samples. And with the LCT, one can only measure 1 sample at a time. And in addition to the commonly used characterization techniques, Linseis offers also another product line which perfectly matches the needs of thermoelectric material investigations. With the Hall characterization systems, shortly HCS, shown here in this image, we offer the possibility to measure the Hall constant with a high accuracy. And the Hall constant can be used to calculate the charge carrier density and Hall mobility. In addition, the sign of the Hall voltage indicates the type of majority charge carriers, where a negative sign indicates electrons and a positive sign indicates then holes. So the knowledge of the charge carrier concentration is very important for research on thermoelectric materials, as the ZT value strongly depends on it. This can be seen here in this image. So the ZT value, shown with the green line, depends strongly on the carrier concentration of the material. Linseis offers 3 different Hall characterization units with either permanent magnets, a more powerful electromagnet, or with a rotating Hallbach magnet, which allows an oscillating magnetic field. And all of these 3 setups are equipped with an integrated and optimized measurement electronics and can be upgraded for high temperature measurements up to 700 centigrade Celsius, as well as log-on amplifiers for noise-reduced AC measurements. And another very important, also recent trend in the field of thermoelectrics is the investigation of nanostructures, as they can possess some very unique features which are advantages for thermoelectric applications. On the one hand, additional charge carriers and phonon scattering within thin films or nanowires can increase the ZT value by suppressing the lattice thermal conductivity or increasing the power factor. And on the other hand, the production costs can be reduced because thin films simply need less material and can easily be scaled up. And generally, it counts also that the properties of thin films can vary significantly from the bulk material. Linseis offers for that 2 standalone systems, especially dedicated for the characterization of such thin films. There's the thin film laser flash analyzer, here shown on the right. This one can measure the cross-plane thermal diffusivity, similar to the LFA, but especially for thin films from the nanometer to the micrometer range. Additionally, there's the TFA, the thin film analyzer, here on the left, which is the world's only integrated system which allows a comprehensive characterization of thin films in the plane. It can measure the Seebeck coefficient, the electrical conductivity, or in more detail, the electrical resistivity, the thermal conductivity, the specific heat capacity, and the Hall constant of nanometer to micrometer thin films. So this means with the TFA, one can make a full analysis of the thermoelectric properties of a thin film. Now, after inventing promising thermoelectric materials, the next stage is the finally developed and assembled module, as shown here in this image. And for this, Linseis offers the TEG tester, which is a device to measure the conversion efficiency of modules under real-world conditions. A TEG tester is shown here on the lower left. And for the measurement, a variable heat flux can be applied to the module under defined conditions, like, for example, contact pressure or ambient temperatures. In addition, the corresponding output voltage can drive a variable load, and this procedure is called maximum power point tracking and is a commonly used technique to characterize the real performance of energy generators. Next to the overall conversion efficiency, the TEG tester can also be used as a thermal interface material tester. In this configuration, it would be then called TIM tester, shortly for thermal interface materials tester, and with which one can analyze the thermal impedance of the utilized contact passes for the TEG and for optimizing the thermal contacts of the top and bottom ceramics to the thermal elements. For the same topic, a DSC, shown here, and which stands for differential scanning calorimeter, can be used to determine aging effects under temperature influence, for example, of the contact passes. In addition, a DSC is the most commonly used instrument to determine the specific heat measurement, which is useful for completing the laser flash analysis for determining the thermal conductivity. And the LFA, as already mentioned in a previous slide, can also be used to characterize the ceramic plates, which are typically on top and on the bottom of such a TEG. So until now, I showed you different instruments which can be used to characterize different thermoelectric materials. But what are thermoelectric materials? As already mentioned, for a good efficiency, one can characterize thermoelectric materials using the figure of merit, there's a T. And according to the formula, one needs for a good efficiency a material with a high electric conductivity, with a low thermal conductivity, and with a high Seebeck coefficient. Thermoelectric materials, good thermoelectric materials are mostly semiconductors and semi-metals. The good properties refer to the band structure of these materials. So this can be also seen here. So the figure of merit is the highest in the region of semiconductors. Furthermore, the performance of semiconductor as a thermoelectric material depends also on the carrier concentration. The carrier concentration I just mentioned before can be characterized accurately with an HCS. So this means For a good efficiency, one wants to maximize the power factor. The power factor is here the numerator of this formula, and one tries to reduce the thermal conductivity as much as possible. And for this, there are many different approaches, for example, alloying or the implementation of additional scattering sources in form of nanoparticles, superlattices, or composites. These have been investigated and developed in a high amount. And here on the lower left of the slide, you can see a few examples of thermoelectric materials with their figure of merit in dependence on temperature. Here, for example, you can find bismuth telluride, which is a well-known thermoelectric material. And for example, an alloy of bismuth telluride, one can find here zinc antimony or silicon germanium. So here one can also see that the performance of the material strongly depends also on the temperature. Thus, for different applications, different thermoelectric materials are suited. And now we come to some application examples. So here on the top, you can see an example for a resistivity and Seebeck coefficient measurement done by LSR of a silicon germanium alloy in a temperature range from 50 centigrade Celsius to about 270 centigrades. And here one can see that the resistivity of this material is increasing with temperature, and the Seebeck coefficient firstly slightly increases and then decreases with temperature. So on the right, one can see also a measurement performed with the LSR, but here the Harmon method was used to direct measure the ZT value of bismuth telluride. In this example, you can see here the ohmic drop of the material and the thermal voltage. This measurement was repeated again with negative sign of voltage, and both ZT values were then averaged. So here one can see that they're nearly the same, and on average something about 0.5 for bismuth telluride. And this measurement was performed at room temperature. So for a temperature-dependent measurement, one would need to repeat this measurement at every desired sample temperature. Here are some examples for measurements with the TFA. As already mentioned, thin films can show lower thermal conductivities compared to the bulk material, while the electrical conductivity and Seebeck coefficient are much less affected by minimizing the thickness of the material. So this means that there's a T value will be higher in consequence for a thin film compared to the bulk material. On the left, one can see an example for bismuth antimonies. Here, the thin film had a layer of 84 nanometer, and you can see the full thermoelectric analysis of this nanofilm. So the Seebeck coefficient was measured, which increases and decreases with temperature. The electrical conductivity was determined, which is increasing with temperature, and the thermal conductivity was measured as well. Here also the values increase with temperature, and from these properties the figure of merit could be determined, which you can see here with the orange line. You can see that the figure of merit is increasing with temperature, and slightly decreasing here at the higher temperatures of this measurement. The maximum found value of this measurement was about 0.16, and this point was measured at room temperature. On the right, you can see an example of an organic conductor and thermoelectric material, which is called P2PSS. This layer had a thickness of 15 micrometers, and with the TFA also a full thermoelectric analysis was performed. So again, the Seebeck coefficient was measured, the electrical conductivity was measured, as well as the thermal conductivity. With these properties, the ZD value could be determined, which increases in this example with temperature. On this slide, you can see also a full thermoelectric analysis of bismuth telluride samples. One of them was N-type with selenide, and the other one was doped with antimony and resulted in a P-type material. But this analysis was not performed with only one instrument. Several instruments were used for the analysis. So the LFA was used to determine the thermal diffusivity. The measurement was here performed from room temperature to 300 centigrade Celsius. Here you can see that both materials behave similarly, only the values differ. So the N-type material shows here higher values. The specific heat capacity measurement was performed using a DSC. The temperature range is here the same. And one can see again that the N-type material has higher values. And additionally, one can see that the behavior of the specific heat capacity of the N-type material differs from the P-type material. The LSR was used for the electrical resistivity and Seebeck coefficient measurement. And here you can see the results. So here for the resistivity, the P-type sample shows higher values compared to the N-type material, and the Seebeck coefficient is nearly the same for both materials, only the sign is different. So with all of these measurements, one could determine on the one hand the thermal conductivity using the thermal diffusivity and a specific heat capacity measurement. Here you can see the result of it. So both behave similarly, and the N-type material shows higher values. Combining then the thermal conductivity results with the resistivity and the Seebeck coefficient measurement, one can obtain then the figure of merit, the T value, where one can see that the P-type sample has higher values, but at temperatures starting from 150 centigrade Celsius, both materials show similar values. Only in the lower temperature range, up to 150 centigrade, the values differ more significantly. So this was all from my side. I would like to thank you for your attention. And in summary, I presented to you different instruments which can be used for the characterization of thermoelectric materials, which are mostly the LFA and the LSR. And this lineup can be added, for example, with the HCS, the DSC, or for thin films, also the thin film analyzers.